I've got the FX201P here with the Pico emulating both RAM chips which have been removed. There's sockets there so I can put them back if I want. And the code, I've done a bit more code and investigation, and if I turn this on, I need to press the AC key at power on because that synchronises the clock. The memory chip enable is held low all the time, which is a bit of a problem, and my code needs to synchronise to the RAM, so it's not a huge problem. You just press AC when you turn it on. If I run the program, you can see there's nothing attached, it's powered off batteries, but there is a program in there which is displaying some characters from the full character set. I think I'll turn the lights off again there so you can see. It's actually saying I lose. If I hit answer, let's put this light on here so you can see the display and the keyboard. There you go. So in the other memory 2, I've got the extra characters which you can display. It's not a particularly useful range of characters and symbols on here. It's not quite as good as the Pro 101, but you can actually use those as prompts and things if you wanted to. But I've organised this so that flash slot 0 is loaded when the calculator's turned on. So ordinarily this comes up blank, but if we go into program mode you can see that there's a program there, and if we go back into manual mode you can see that I've loaded some memories 1 and 2 with the characters from the extra character set that you can display. So this now effectively has got, as long as you press AC when you turn it on, has actually got non-volatile memory. So the memories and the program are actually stored when you turn the machine off. You can change whatever you want it to come up in, because slot 0 is just loaded by default when the thing turns on, and whatever you put in slot 0 is the data that will appear when it powers up. So I'm going to attach the USB here because I've changed some other stuff and investigated to see what the calculator does. So if we go here, that's the new menu with some extra facilities. If I look at the slots, I've got some labels and some programs here. So 240 and 241 are quite interesting. So if I 240, load 240 up and display that. So this is a program which adds 1 to memory 3. You can see that here. But it's also got some extra stuff, and what this does, this bit of code at the top here, this line, that is actually going to switch in, or well, that's actually going to execute a command. So memory 8 is where you put the commands which talk to the Pico and do various things. So whatever you've got in memory 2 will get copied into memory 8, and if that's a command it will get executed at that point. So when this program starts up, it just runs through this line, puts whatever's in 2, 0, into 8, nothing happens because that's not a valid command, and then it goes to 1 and runs the main bit of code here. And what that does is add 1 to memory 3, then it puts a command in memory 2, and that command is actually a command which tells the Pico to load up slot 241. So this is slot 240, and this is saying load up slot 241. You go to 0, it executes this, and then at this point here it loads in slot 241 now, and then executes whatever's in 241. If I load 241 up, I'm doing this just through the USB because it's a lot quicker. If you load 241 up, you can see it's got the same first few keystrokes, and that's a bit like bank switching. It's the common area in a bank switching system. Then it runs down here and increments memory 4. So the previous 240 program, the program that was in slot 240, increments memory 3, and then quite predictably it runs a command which loads 240 back in. So what this is doing is loading slot 240, you run it, it increments memory 3, and then it loads slot 241, slot 241, when it executes, increments memory 4, and then loads 240. So it alternates loading 240, 241, and also incrementing memory 3 and memory 4. So we've currently got 241 in there, it doesn't really matter. If I come over here and start this up in the correct mode, comp mode, so that's now running, and you can see that slot 240 and 241 are alternately being loaded by the Pico. And that happens so fast that the let's just have a look at the memories first. You can see that 505, 507, 18, 19, 20, 21, 22. You can see memory 3 and 4 are incrementing. I'll stop it because the display is a bit irritating. So you can see that this is chaining programs. You can extend the program space of the 201 by having different slots with code in, and then load in whatever you want to execute next. This common area here is quite handy because the swapping of flash is actually done when this executes. When memory 8 is seen to have a command in it of the correct format, that will be executed by the Pico. So at this point here, around about the time that the colon's being executed by the 201, the Pico has swapped the memory in from one slot to another. If you make the first part of each of the slots this same bit of code, then it doesn't really matter whether the Pico's halfway through loading or not, because the 201's only going to be executing the same steps. Doesn't matter which slot. You could have half of one slot and half of another, and it would still execute correctly up to this last colon here, obviously, or maybe actually up to this label here. And that gives the Pico plenty of time to load in 256 bytes from flash. That's pretty quick. So that's a way that you can extend the memory and use the slots. At the moment, 250 slots, each with memories and code. I've got different commands now. If you look in the menu, I've got different commands. You can save and load the whole emulation RAM here, or you can save and load just memories or just programs. So you could switch in different memories, switch in different programs, and leave the memories there. So that gives you quite a lot of scope for extra programs. I think as well, with some more elaborate code, you could probably because of the way that the flash is organised, you've got to erase 4K at a time. But if you save it, change it, and then write it back after you've erased it, you could probably, with some more complicated code, get up to several thousand slots, several thousand 256 byte slots. The full memory that I've allocated to the data storage for the calculator is 1 megabyte out of a 2 megabyte flash, so you've got a lot of space in there. So as it stands at the moment, this is effectively equivalent to a Casio Pro FX1, the calculator with the card reader, with 250 cards. You can store memories on these cards as well, so that's pretty good, and it's all in a smaller form factor. This calculator is smaller than the Pro FX1 because it doesn't have the card reader at the top. So it's also non-volatile. You switch it off and back on and you're back more or less where you started, assuming you've saved the data. You do have to save your data to slot 0 before you turn it off, so that's a little bit of a disadvantage. I've also found that if we go here, I've also found out what some of these numbers are. So I found out what these numbers here are. Now the first 10 slots here are the memories, and you can see I've decoded them over here. That's the value that is stored in each of these memories. This slot here I thought initially was actually a memory, but turns out it isn't. So these memory areas here are actually a sort of index table for these labels. So when the program runs, it actually builds up a table of where these labels are so that the jumps are faster. It doesn't actually have to scan the program to find out where label 1 is to do the GOTO 1. It's done that just after you press the start key. So if I can do this, it's fairly tricky. If I let's have a look. If I load in another program, so we've got a program there. So this is quite a simple one down here. All it's doing is incrementing memory 1 and memory 2. So we can execute that on the calculator. If we go here and start running it, and now display the memory, you can see memory 1 and memory 2 are incrementing. So 5662, 33, 35, and they're both counting up, as you can see in the program. Quite straightforward. We'll keep that running because we're going to fiddle with things while the calculator is running the code. So you can see that that is the offset in the program of ST0, and that will be 1, 2, 3, and that is 4. Now that's the actual label we're using to do the loop. You can see down here it's ST4. Now that is 2 times the offset into the program. I'm not entirely sure why there's a factor of 2, but it's 2 times the offset into the program steps. So down here, so it's actually a 1. I think it uses this byte here to actually store or use as an offset. So 2 is the actual index that it uses for the first ST4 here. Now what I can do is, I know where this statement is, so I can tell the calculator to not use 02 as the index, but instead of that use 22 as the index, which is here, over here. And now that will cause it to, instead of looping back to ST4 here, it'll actually loop back here, and it will skip this instruction here altogether. So if we do that, if we go into 4, so 84 is the address, and if we put 22 in as a value and we write that, we can now see we've got 16 here, and the program has carried on executing. There's no error come up. But if we now have a look at what's going on in the memories, you can see that memory 2 is incrementing, but memory 1 isn't. That has stopped incrementing because the calculator's coming over, seeing the GOTO 4 here, whoops, and then jumping here instead of here. And that was done while the calculator was executing the program. It had no idea that the memory was changing. So what I can do now is I can put it back to 2 and write 2 in there. There's a 2 now instead of the 16 or 16. And now if we have a look, it started incrementing both values again. So you could probably have, well, I've actually, what I've done here, I've actually got a GOTO which is jumping to a position in the program that doesn't have a label, so you're no longer really limited to the 10 labels, the 10 STs, step presumably that is, to the 10 ST commands. You can actually jump anywhere in the program you like. It does mean you'd have to edit this byte here, but I do have a command where you can alter any memory location in the emulated RAM, and you can do that while a program's running. A program can do that. So that's different to the Pro 101 because I only replaced the program memory on that. This is replacing the program and the memory. So we're emulating all of the RAM that the programs use. Now, I thought I'd be able to use these extra locations here as extra memories, and you could, if you didn't have any jumps, then you could probably just write into here and store values in there. But these 2 lines here are definitely indices into jumps. There's the 10 ST jump labels, and that's followed here. That is actually the manual jump offset. and you can change that and get the manual jump to different places depending on what value is actually in that byte there. What you can also do is you can change the ST4 to be an STA, and that behaves just like a manual jump, because STA is actually 1 after 9. 9 is here, and that is the manual jump. So you can change that byte using an STA and a GOTO A. That'll actually write the offset in there. So that's just a sort of redundant way of doing manual jumps. I've also got a trace now, which is what I did on the Pro 101. You can, if I start it off, it's running a program at the moment. If I look at the trace here, I've got 2,000 transactions are actually stored. What it's got, that's just a step number in the buffer. Here you've got the address, and then you've got the data, and you've got whether it's a read or a write. So 91, that's reading the program, and you can see it's actually reading instructions here. And then down here you've got a write to 10, so that's writing to a memory, and you can see that there's 8 bytes, and you've got the correct format. You've got the F1 at the start with the sign bits in it and the exponent of 3. So you can actually watch the program execute. Unfortunately, I can't have reads to memory. You can have writes, there's writes here, and you can have reads and writes to program memory, but you can't read, or you can't trace read accesses to the memory IC, because for some reason the hardware keeps the chip enable low on the memory IC, and that means it will be flooded with reads. That's about it really. It's been interesting going through and having a look and seeing how the calculator actually works. I've got a PCB sent off, so that should come back, which means this will become much more like the original calculator. Hopefully I'm going to be able to put my circuitry just in here in the socket, and then the whole thing will be battery powered, and all the commands, or most of the commands that you can do on the USB CLI, will be accessible from the keyboard of the calculator. Obviously the tracing, you can't display the trace on the display, I've got no way of doing that. But saving and loading flash areas and reading writing bytes, that's going to be available from the keyboard. So really it sort of turns it into a sort of smaller, slightly different Pro FX1, and you've also got non-volatile storage, so that it's like a 202 as well really. But I don't think the 202 stored the memories when it was off. This stores the memories as well, so you can store data or programs.